So, hello everyone. This is day 4 of the 12 out of the 12 days of NeurIPS. And today we are going to talk about the scaling law. So this is going to be a smaller presentation. Not all of them are going to be 45 or an hour long. So I think a lot of people are familiar with this book. The Singularity is Near by Ray Kurzweil. So Ray is kind of like a futurist. He likes talking about what is going to happen in the future. I think he also came up with a book called The Singularity is Nearer or something like that. So we are about to hit the point where AI is as good as one human brain. And, at some point in the near future, some of us will be alive to see the, AI being better than all human brains. This is coming from a talk. I think this is one of the talks that you should watch. A match made of silicon in silicon from the head of AI at Microsoft Research. But that's kind of like a scaling law that people think in terms of intelligence. And of course, this is the scaling law in terms of hardware. And, I mentioned that before. We are, hardware is hitting the limit. Like if you follow Moore's law, we're about 1 trillion times faster than we used to be in the past. And scaling laws is the way that we move the needle in AI. So let's, read these two statements. One is from OpenAI. We study empirical scaling laws for language model performance on the cross entropy loss. The loss scales as a power law with model size, dataset size, and amount of compute used for training, with some trends spanning more than 7 orders of magnitude. That's how we got into ChatGPT 4.0. Probably that's not going to get us to 5.0. And then this is kind of like the scaling folklore in systems. You can't just keep scaling by throwing hardware at the problem forever. Scale exacerbates hidden flaws and inefficiencies. Everything fails at scale. Scaling is becoming sublinear, and scaling requires revisiting assumptions. So we're going to see how AI is following this kind of empirical laws. And I mean, you might have already seen one. Maybe DeepSeek revealed that scale exacerbates hidden flaws and inefficiency. So people kept throwing more and more parameters to scale language models. And then I think first Llama started showing that you can do the same with less, and DeepSeek, with even less. And we're going to see people are, of course, at some point, it has become the theme over the whole NeurIPS over here. I think this is what could be the theme of the whole NeurIPS here, is that, okay, you got to be more careful about what kind of data. Just don't just get C4 and throw it to pre-train, and do better cleaning, and rethink about how you're doing attention and tokenization, and that's how we progressing. This slide is from the test of time, sequence to sequence learning with neural networks from Ilya Sutskever and the rest of the team. And basically, they're saying that the day or the age of pre-training is probably over. This is what we learned from the OpenAI papers here. And this paper has been cited a lot in this NeurIPS. It's from OpenAI as well. And that's basically reflects the saying that we saw before from OpenAI. And looks like that these scaling laws are not really valid anymore. Like they started becoming sublinear. Now, this is also an interesting talk, synthetic tasks as sandboxes for attributing model. I mentioned that before. This is a workshop that basically tells you how the XOR problem, which is the simplest parity check problem, help us invent the second layer or the multiple layers in deep learning, which was a big moment. And in this paper, they're basically trying to solve some more difficult parity problems and trying to find out how language models are scaling and what we need. And this is an interesting law. You know, if you really want to predict the test performance on compute and data, I think it refers to some specific problems. They came up with this law, which is very interesting. I think that's what I'm saying. We started becoming more quantifiable. Again, we saw the same scaling curve from a workshop or tutorial that we've talked about, I think, at day 2. Where I'm trying to show over here that this was a recurrent theme. You've already seen 3 or 4, and I'm pretty sure there's even more presentation talking about that. This is a talk from Meta talking about how they were able to scale Llama. And this is their scaling curve for building Llama. And again, this is, I think this is coming out of for OpenAI. And again, now people seeing how models are scaling by giving them more test time compute. Okay, now that was another interesting paper. I think I've talked about that tutorial again. This is Allen Institute talking about how we can build a language model from scratch, and they open up. This is a truly open source language model where they show you everything they did with all their challenges, and this is how they estimate the capacity, the optimal model size. I had the legends. Oh, here it is. So N is the number of parameters, D is the training data and tokens, and C is your compute budget. So, you know, if you have a compute budget and data budget, you can find out how many parameters you need, and the opposite. So again, another empirical law when you design language models. And here are the references that I particularly enjoyed this one. Go small or go home, where they basically argued that, you know, you might actually need a smaller LLMs on more tokens. That's an interesting approach. Here's another kind of like interesting paper with the title, "Why has predicting downstream capabilities of frontier AI models with scale remained elusive?" And again, you probably have seen, it's another time that you see this this plot again. And you know, the authors, they give their kind of like point of view over here. And I don't remember what's the, let me see if I have it here. What was the outcome? I'll take it on me. I read it at some point, but I've forgotten it. Here is another interesting paper that kind of defies the rules. So every time you have rules, you have some exceptions. So we kind of know that if we can take, you know, enough model, you know, enough data, a big model, you pre-train, you get pretty good tasks. But there's surprisingly a task which has to do with sentiment, okay, where they basically show that, you know, they call them perception tasks. Is LLM pre-training by next token prediction worth its cost? So they basically ran extensive experiments, and they saw that it's better to just take a model and train it on your supervised data and avoiding pre-training. And that has to do with perception. I think there's something behind that. The authors don't explain why, or they don't really know why, but I think it's an interesting exception to be investigating. So anything that has to do with perception, sentiment, it's much better to train a smaller model in a supervised way and avoid pre-training. And again, pre-training has a big cost. Here's another paper that I think I've talked about before. It talks to the neural scaling laws. And this one is a little bit technical, so I have avoided to give more details. So it talks about the neural scaling laws. And it has a lot of, it talks a lot about the geometry of data. And we're actually going to spend the rest of our time talking about this. I think I've said that before. One of the best talks at New Rips is "It takes a village to grow a strawberry." This is kind of like how they got into the O1. So this is from Noam Brown, and again, farming in the LLM era. And you know, again, the author starts here talking about the cost of training GPT-2, $5,000, GPT-3, almost $1 million. And then we don't really know the money for 3.5. GPT-4 is estimated 50 million. And it just takes a simple question. It's a simple reasoning question, and you know, it gets confused, incorrect, and after spending 50 millions, you get it correct. The problem is that compute becomes you know, super big, and the question is, would you pay trillions of dollars for better AI? So that's where this whole idea from the scaling kicks in, that we saw before from the systems folklore. So maybe we can do better. And this talk is all about the history of poker competition, and how Noam was a student at CMU, and he made it in the news because they managed to beat the poker competition. And says each year research labs would make poker bots and play them with each other, and it turned into a competition of scaling models. So basically, they realized you throw more parameters in your model and you score better. So let's see what happened in 2015. We CMU challenged 4 top poker professionals to an 80,000 hand poker competition. I don't know much about poker, but I guess that's something challenging. $120,000 in prize money to incentivize them, and their bot lost to that cost. They explained it in the talk, but I don't understand, but it was pretty bad, Claudico. And you've seen that plot before. They realize that you know, people, when they play poker, they don't respond immediately, but they spend some time to think. Okay, so this kind of like an interesting plot basically tells you for the same number of parameters, if you give it, I think it's about 30 seconds, you get 8 times better. And this is, you know, this is a big gap you're getting by just doing some search with the same model. That was huge, and basically that observation changed the turned the tables, and now they won by 15 BB out of 100. I don't know what it is. And before they had lost with 9 BB out of 100. And you know, there's apparently some statistical significance, and each human lost individually to Libratus. That was a new model, and obviously it made the news. I think that's probably a Nature paper. Let me see over here. I think so. That was a big success, and that was by giving more test time compute. And similar story actually exists in Bagamon, and it goes, you know, Bagamon is probably easier, and you know, of course, achieved Human Master Level 1994, and it used 2 to 3 PLY, I think it's player search, in addition to its neural network. I believe there's also a book. I need to go and search for that, called Blondie 21. That's I'll add it later. That talks about beating Bagamon. I think there's an interesting story by someone who was at a hedge fund and he was playing online, and he deliberately named his player Blondie 21 to appear that it's I don't know, it's going to be an easy player. And here you can find the paper. Took some time to find the paper. And same story goes to the game of Go that I think most of us know with deep learning, with reinforcement learning. And you can see that if you put, so the 4000 ELO is the superhuman performance. You don't put any test time, you're not doing well. And then the different versions of AlphaGo. I don't know what the variations are, but this is the full AlphaGo 0. And that's interesting that you can increase the ELO by 120 points either by doubling your model and training, which is huge if you think about how big these models are, or by doubling the test time search. And here's the very interesting, I think we should really stick into that sentence here. To get the raw policy net from 3000 ELO to 5200 ELO, you would need to scale by 100,000x. So you can do that by putting more time or more hardware. You can take the log of that and you can see, I don't know, what's the log of 100,000? That's how much you would have to double your, how many times you would have to double your compute or give it more search time. I think it was a combination of both here. We've seen this curve again. This is about scaling laws with board games, and kind of like the same empirical row. So for each additional 10x of train time compute, about 10x of test time compute can be eliminated, or the other way around. Okay, so you can make it 10 times slower and give it 15 times more time. And here they make a reference. That was an interesting paper. It wasn't presented at New Rips. It's called Large Language Monkeys. So basically, this is how you can scale inference compute with repeated sampling. But just remember that in these games, you have a heuristic function that you're telling you how close you are to winning the game. So the easiest thing you can do is, you just sample your language model for 30 seconds, how many times you can do that, and you see which one is giving you the best scoring function. And Amy is a specific benchmark for O1. So this is the accuracy train time compute log scale. So train time compute is equivalent to model size, basically. Okay, and here is if you give it test time compute. So you see that the test time starts lower, but eventually it catches up and it becomes even better, even by using less data. Now, again, I'm going back to the DeepSeek paper. It's kind of difficult to avoid. We have to. It's part of the time. Like if I was giving that presentation a month or 2 months later, who knows what I will have to reference. But this idea that chain of thought prompting elicits reasoning in large language models, this idea that if you uses large reinforcement learning to generate a chain of thought, that idea that if you use a reinforcement learning fine-tuning or training, chain of thought will be something that is going to emerge. So that's something we already knew. Okay, I think DeepSeek made it more more prominent. And in fact, it's funny because O1 was before DeepSeek R1, but DeepSeek R1 didn't really, Strawberry O1 didn't really talk much about it. Okay, they didn't. I think we talked about before. OpenAI chose not to show the chain of thought because they were afraid it might say something inappropriate and didn't want the liability. And here's some properties. Chain of thought contains behavior like error correction, trying multiple strategies, breaking down problems into smaller steps, examples of chain of thought on the research blog post here. You can, here's what you can learn from OpenAI. This is the post. And, here we keep talking about the verifiers. And for some problems, verifying a good solution is easier than generating one. Here are some example, many, Sudoku, math, programming. Example, verification isn't much easier, like information retrieval, image recognition. When a generator verifier gap exists and we have a good verifier, we can spend more compute on inference to achieve better performance. So that's why, for example, DeepSeek R1 is not as good as information retrieval as, 4.0 is, because here, we're missing the verifier. So we have to spend more time on train. That's like a very nice insight. I like the way they phrase it over here. And this is the frontier math. We're going to see that in the Math AI workshop 2 is a new benchmark, very difficult. Okay, you can you can tell. I don't know if any of us here, I hope, but I can't. I don't know how to solve that problem. This is the type of the problems you see in frontier math. And you can see how bad the performance, like, we're way behind. We're probably more than the average human intelligence. I don't know how many people would be able, but when we compare with mathematician, we're not that great. So here's how we're going to close for today. Where does this go? Much higher inference compute, but much more capable model. Okay. What inference costs are you willing to pay for a proof for the Riemann hypothesis? So are you going to let your model do chain of thought for an hour, a month, a year? What inference cost are you willing to pay for a new life-saving drugs? I think it starts becoming an ethical problem, the way that they're posing, and I like that. This is a different line of ethics in AI. Like, are we going to burn a village, or put another, I don't know, million tons of CO2 in the atmosphere in order to cure cancer or HIV? They do believe that there's still room to push inference compute much further, and AI will be more than chatbots. So I'm going to stop here a little bit, 5 minutes earlier. Let me see how I stop recording.